What we're going to be talking about today is not the daily data entry, but we're focusing on the pre-meet inspection, and in particular, the issues associated with the grades and design of the track. A lot of this documentation hasn't been standardized, and this is, again, just like everything else we've seen with HISA, we're beginning to think about how we can standardize this and understand the risk, because this is important to the safety of the horse and rider. So the first person who's going to talk is Branden Brookfield, who is going to talk about what to expect when he comes to the track to do the pre-meet inspections. So the pre-meet inspections are done typically 2 to 4 weeks before you start racing. You have to be ready for racing. The surface has to be ready. A series of tests are done. If you have a long meet, if you have essentially, a parks or one of the really long meets, you do it before the start of the winter and before the start of the summer, especially if you're changing over the track and, recovering from the spring where you had to add a lot of salt. Kaleb Dempsey then is going to talk about the specific information that you're going to receive as a result of that testing. You'll get a report. That report, the data is automatically fed to HISA electronically as raw data, but you'll get a report that has a summary of all the information from your track. And going into next year, you'll get some comparisons to other tracks that'll help you understand how your behavior, your track compares to other tracks. Roderick Saylor, who's over here, is from GRW Engineering. He's going to talk about what you need to do from an engineering standpoint. A lot of what the engineering end of this would be a new track or a major renovation. That's an excellent opportunity to sort out the documentation. And then the last speaker is Dean Johnson, who is a surveyor. Dean and Roderick are engineers and surveyors. Everybody has an engineer and surveyor nearby, but what I tell people is you don't have to tell either one of them that the horses turn left. And they have specific knowledge related to horse racing. The final part of this is we have an award that we're giving. It's the 4th person who's received this award, and a particularly deserving one. So I'm going to pass it off to Branden Brookfield.
Morning, everyone. As Mick said, my name is Branden Brookfield. I am the on-site testing manager with Racing Surface Testing Laboratory. And today I am really going to go through what on-site testing includes and what that is going to look like when I show up on your racetrack. So starting out, why does our on-site testing look like it does? And so a lot of what we have been doing, especially these last year, is pre-meet inspections. We are showing up, as Mick said, 2 to 4 weeks before your race meet starts, and we are going through and trying to fulfill each of these. And so as we go, so we are going to be looking at geometry of your track. We're going to be taking grades, looking at the slopes. We're going to be trying to figure out the accuracy of the distances. We can GPS mark your poles. We're looking at cushion and base geometries. We're taking those measurements at every 8th pole as we go around. We're doing a base inspection. We are using ground penetrating radar to do that, where you are not having to take a large windrow out of your track to get down to your base and inspect it. And so we're being able to look at it that way. We're looking at the mechanical properties of your racetrack using the orthobiomechanical surface tester. The surface materials, we're going to collect some samples, take it back to the lab, and you'll get a report on that as well. And then we are also trying to fulfill these 2 bottom mandates here, the rail inspection and the track design records. And so this is all for the dirt and synthetic. For the turf, it's just slightly different. Mostly looking at the turf profile and turf species. We also want to take some samples there. And so then how are we fulfilling these requirements? As I said, we're using the orthobiomechanical surface tester to look at the different properties of your racetrack, how it responds. That machine is going to be replicating the leading forelimb of a horse at a gallop. And so it is a standardized way for us to test across many different racetracks. Again, the ground penetrating radar, where we can look into the layers of your track and not have to do anything really heavily invasive. The rail inspection, we're going around, we're walking the surfaces, making sure that everything's at a relatively standard height and that we don't have anything like we see here where there's gaps. And then we're doing the surface cross falling grades as well as checking the marker poles, as you can see there in the far right. So first things first, when we make it to your track, what do we need? We need a race-ready surface on your dirt or synthetic. And so what is a race-ready surface? A race-ready surface for us is going to be prepared as it would be for your first post. We don't want any changes. We want to make sure that you've really got all the hoof prints out if you've had morning training, and that everything is as set up and as perfect as it can possibly be. The biomechanical tester, we call it the OBST. It is fairly sensitive to changes. I mean, we're looking at variations of a 1/4 inch and seeing disparities with that. And so we really want to make sure everything's set up as best it can. Also, we would really appreciate that we don't have a change in daily routine. If you change the depth on your harrows, you change the speed at which you're driving, you can start to create problems, which makes it not as accurate a representation of your track as you would probably like. And then we also need it to be classified as good. We can't test a sloppy surface. I don't think you guys would want us to test on your sloppy surface. It's just not going to give any good data. And so to start out, we usually begin with the OBST. We are doing 3 drops at each 8th pole in the 7-foot and 15-foot lanes of your racetrack. And so you can kind of see that here. Your blue is going to be your 7-foot drops. Your white is going to be your 15-foot drops. It's 2 laps. And that'll take us roughly an hour to get done. And so why are we testing at these locations? Well, it's going to accurately represent your racetrack for what most of your horses are going over. You know, it's racing lanes. We want to be down there closer to the rail. And that is really what we are concerned about, is when your horses are up at speed. Testing at 7 and 15 really make sure that we cover that. You know, if you've got larger field sizes, if you've got 10, 12 horses running, you're obviously going to be out just a little bit farther than that 7-foot location. And the 3 drops at each location really just allows us to look at variation both there at the pole and then variation over the entire track. And so what information is our OBST producing? You're going to get 3 different measurements that are going to be in your on-site testing report. You're going to have your cushioning, which is your vertical load. You're going to have your impact firmness, which is the deceleration. That's going to come to you in a G-force. And then you're going to have slide, which is your horizontal. And so all 3 of those will be, you'll be able to see how your poles stack up against the points local and then across the racetrack. And then for turf, we are actually going to use the penetrometer, which is a little different than the OBST, but a very similar concept of looking at the penetration depth. So the next thing we're typically going to do is we're going to go to the ground penetrating radar. Once we have finished with the hoof tester. And so for that, we would prefer that the surface be sealed in some capacity, whether it's with a roller, you float it down. It just makes that antenna bounce a little less. That's going to be the white piece there. And so the less that bounces, the better it's going to make your track look. Obviously, this is going to be able to see down. We can see your cushion layer. We can see a pad layer, hard pan if you've got it, and we can see your base layers. And we can do all that without having to really disturb the surface. But having that nice, smooth ground to go over certainly helps us get that image better. And the best part that we like about this is it allows us to take an extremely large amount of data in a relatively short amount of time. from us dialing it in to being done takes roughly an hour per surface. And we are taking a measurement at every 4 inches around your racetrack as we drive. And we're going to do a total of 4 laps. And so that's obviously quite a bit of data points. It's a lot more than you could do taking hand measurements out there, and it's much more efficient. And so what does this produce? For us, we're going to see this picture here when we go through to process this data. As you can see here, the cushion layer, which is going to be these smaller yellow dots at the top layer, it's roughly about 3 inches. We've got a scale on the left-hand side there. We can also see the base layer here at roughly 8 inches. And so we're going through and looking at these layers, we're trying to see anomalies. If we see anomalies and things in there, we can notify you guys, and we actually have it with GPS data, and so we can tell you exactly where on your racetrack that is. It's not a guessing game. It's not, okay, it's roughly at the 8th pole. We can tell you fairly specifically where that's going to be on your racetrack. And so then after processing the data, you guys are going to get a much cleaner version of this. This is not what you'll look at in your report. You're going to get a nice overlay of the track with a color map, which is going to be a little bit easier to read than trying to go through here and look at 5,000 feet of data points. So after we get done with that, and this is the part where I like to say that you guys can really have your racetrack back. Normal maintenance can resume. I can dodge you and really make sure that I'm out of your way. And so I understand. I worked on crews at Keeneland. I understand you guys have a lot to get done. And so in roughly 2.5 hours of the testing, you guys can resume your normal maintenance and really get back at it. And so as you guys resume, I'm going to be taking grades. And so we are using just the tripod laser here, and we are checking it at each 8th pole. And we are just checking crossfall. We're not necessarily doing rise and fall of your racetrack. We are checking crossfall at the pole locally. And so we are going to do that in 10-foot increments. That's, I think everybody in their folder has the data sheet we use for that, correct? And so you guys can kind of open that and look there. We're going to check it 0, 10, 20, and 30 so that we can see your grades as we go across that inside racing lanes. And then this is what you're going to get when we are all said and done. You'll have a very similar picture to that in your report. And it allows us to determine your average slopes, look at standard deviations, make sure that you're consistent around your surfaces. Obviously, that's our goal right now, is consistency. While we're doing that, I'm also doing rail height and pole distance. And so as I'm getting to each 8th pole, I'm taking the GPS location of that pole. For us, we can go back into Google Earth and we can actually plot that and overlay it as you see here on the right. And again, when looking at the rails, we're really just trying to make sure there's no gaps. We've got a standard height somewhere between 38 and 42 inches on these steel in-ground rails that are permanent. And as I said, there's just nothing hanging, no wires or any sharp edges that you could hit. So how is this information going to come to you? You are going to get both of these charts here. It's going to show you the distances between your poles at each 1/8 of a mile here, so 660. And then you're also going to get the rail height on your left there. And so for us, this is a great way to look at consistency. If we have a spot that's different, it means that we probably want to take a little bit more of a look at it. And then obviously the marker poles for you guys setting up the timers and things, it's important to make sure that you have them where you think you have them. After we get done with the grades, we're also taking samples as we're on site. And so depending on your track is going to be dependent on how we take samples. For dirt, we are taking 7 standard samples for anything over a mile and during on-site testing. So if you're a training track, we're just generally hitting your quarter poles, generally a little bit smaller. you can get a much more accurate representation with fewer samples, even though just because of the smaller surface. Synthetic, we're also doing quarter poles at 7. And then the turf, we're doing quarter poles at 3 and 28 as the rail tends to move for most properties. So how are those results going to come back to you? That is going to be a report separate from on-site testing. When I make it back from my trips out to the lab, I'm handing those off to other people within our organization, Pat and Andrew, and they are looking at the salt, silt, and clay percentages of your racetrack and of that sample. The different samples that we take allows us to compare across your entire surface. And so if you have spots that are different or areas that are more affected by erosion, we're able to see those differences and then advise on how you guys can help them. And so, as I said, a huge factor affecting that is going to be drainage of your racetrack. If you've got large drains in an area or a place that continually likes to run off, most of the time that area is going to come back slightly different when we run the tests. And these results are going to be provided in a composition report. As I said, that's going to be set out separate from the on-site testing report, but shouldn't be too long after we were on site. The final thing that I'm going to do while I'm out there is check your weather stations if you guys have got one on your property. Really don't need anything from you all on that, and generally it's not on the track. So I will be completely off your surface at that point. I'm going to be just checking your rain gauges, making sure everything's on, and making sure that you guys are receiving data so that you can make decisions when you come in the morning. If we want to cut the track open, you can open it, see if how much rain you got in the night past, and make that educated decision from that point. And so where are you going to? Okay, the next thing I'm going to do is the maintenance manual. This is going to be something I do when I get back to the lab. It is kind of development of a standard operating procedure for your racetrack. The biggest thing that we see in this is knowing where to find it. And so this is just a snippet of the MQS page once you have logged in. And as you can see, it's going to be right here on your homepage for maintenance manual. Once we have that completed, it will just appear on this. It's not going to be something that's sent out formally to you. And so then what kinds of things are we putting in your maintenance manual? Well, we're trying to figure out how you are taking care of your racetrack. And so we want to know the equipment, the depths, the speeds, how you're running it, certain patterns. If you have a way that you run your brakes or you have a way that you open the racetrack every day, those are all really helpful things for us to note. And then you can see here in the top, this is what your maintenance manual is going to look like. It's going to have your equipment and what it is, how many of them you have, anything specific to your setup. And then the more information that we can get, the more information we're going to provide back as far as what you're doing daily with that equipment. We do this also for the turf. It will be included. The turf, we're wanting to see if you have anything specific to the turf, as far as a turf tractor, aerators, vertidrain. If you have a specific spreader that you like to top dress with, those are all things that we want to include in your turf report. And so just a little bit of a recap here on what the on-site testing day is going to look like. We are going to start out with the OBST on that race-ready surface. It's going to be about an hour and a half for us to get that done. After that, we're going to move to ground-penetrating radar. You guys can seal the track at that point, resume watering if you need. And that's going to take us about an hour per surface. Once we move on to sampling and grade and rail inspection here, you guys can completely have your track back. Whatever maintenance needs to be done can be done at that point. We'll make sure we stay out of your way. And then the final thing I'm doing while I'm there is checking your weather station, making sure that's cleaned out and that you guys are receiving all the data that that's going to provide you. And so then when are you going to get your results? That's probably the question that you wonder the most once we leave. For the maintenance manual, as I said, it's going to appear on your MQS when we get that done. It's typically pretty close to when your on-site testing report is going to go out, and that report's going to go out in about 3 to 5 days. The track sampling and composition results, that takes a little bit longer usually. If I'm out and I have 3 tracks that I'm going to hit while I'm on the road, those samples don't actually make it to the lab until I make it back. And so it's about a 7 to 10 day window on those samples. And overall, that is what our day on-site testing looks like. Do you guys have any questions? Okay, then I will hand it over to Kaleb, who is going to go through the on-site testing report and interpret that a little bit deeper for you all.
All right. Good morning, everyone. My name is Kaleb Dempsey, and I am the Chief Technology Officer from Racing Surfaces Testing Laboratory. And today we will be discussing what you will see on your on-site reports, and more importantly, what does it all mean? So as Branden went over, we have a suite of testing that we perform when we come out and do our inspection as regulated by HISA. So we have the Orno Biomechanical Surface Tester, OBST. We have the ground penetrating radar. We have the rail inspection. We check your pole distances. And we're also looking at your surface crossfall and/or grades. So what is the OBST? Branden went over it briefly, that it's the loads applied by the leading forelimb of the horse at gallop. So that strikes, the OBST strikes the surface with about 2.5 times the body weight of the horse, which comes out to be about 2,500 pound force or 11.1 kilonewtons. So the 3 main variables that we're looking at here, we are looking at the cushioning. That's that peak vertical load. So when the hoof comes down, we're measuring the force, reactionary force of the surface. We're also looking at the slide. The slide will be the resistance force of the hoof wanting to move forward. And then we're also looking at the impact firmness, which is the peak decelerations. And we take all of these measurements and we're going to pit them together and we're going to see what kind of story it tells. And most of everything that we're going to be doing, it is going to come back to be, hey, what are these results looking like? And hopefully what we would like to see is that it tells a boring story, because that would mean that nothing is out of what we would expect to see. So what is the purpose of this testing that we do? This is going to be true for everything. We want to know your spatial consistency. We want to see that one end of the track looks like the other end of the track. We want to see that the inside racing lanes also look like the outside racing lanes. Then we have the temporal consistency. That is, we want to see that when we come in and test your track in the spring, it should look just like it did the previous fall. We also have the ability to see how maintenance practices change. How will that change the response of the surface? You know, if you use one piece of equipment as opposed to another, what is that going to do to the track, and how would that change it? We did this at Santa Anita back in 2019. We also did this back in Laurel in 2021 after they had changed the track over to a new sand profile. They were actually finding that they were having difficulties using the previous maintenance practices that they had used. And so we were able to come in with the OBST, the ground penetrating radar, et cetera, and see how it actually affected the track. And then they were able to make a data-driven decision based on these results and how, you know, how they can manipulate the track to get back to where they want, where everyone's happy. So when you get your OBST results, and actually all of the other results, you know, it can be pretty overwhelming with the amount of data that is displayed and showed. So hopefully by the end of this presentation, everyone here is going to have a little better grasp when you get this report across your desk. So as Brendan mentioned, when we perform the OBST, we do 3 drops at every 8th pole on your inside and outside racing lanes. And those are represented by the crosshairs here. So each one of these crosshairs is a single drop of the OBST hitting the surface. The red line, that is your average or your mean line. So in an ideal world, every single point that we take, every drop would fall on that red line. That would mean that there would be no variation. But we don't live in a perfect world. So what we do is we add in this blue line, which represents 1 standard deviation. So ideally, we would like to see that all of your points fall within 1 standard deviation. So what is a standard deviation? We look at it more of like a probability. So if we were to come out and retest your track, that would mean that we would have a 68% chance that if we retested anywhere on your track, that we would fall within 1 standard deviation. We would have a 95.7% chance that would fall within 2 standard deviations. And I believe it's a 99.7% chance that would fall within 3 standard deviations. So ideally, when we're talking about the standard deviation, the smaller the standard deviation, the better. We also have this p-value here. This is a fitted p-value for what we would call a normal distribution, which is this black curve right here. The closer to 1 that value is, the better. That means that the results are evenly distributed. So, we're not getting a point where we're, skewing up to maybe the track is going to be harder or softer, so to speak. So we would get this nice bell-shaped curve, and that would mean that, everything's evenly spread out. At the bottom of this curve, we're going to have some just your baseline statistics. So we're going to look at the results as a whole, and then you can see that we have our 7-foot results, which would represent your inside racing lanes. And then we have your 15-foot results, which would represent your outside racing lanes. And we present that down here at the bottom of the curve. So here we have the surface average, which in this case for this track was 11.1. We had a standard deviation of 0.9. And so in my previous slide, I talked about spatial consistency. We want to see that one end of the track looks like the other. And so when we're looking at this, we can see that, the grouping, everything is relatively dancing around this red line. We have most of the data points falling within the 2 blue lines, your standard deviation. And we have that represented down here in a numerical format. So we have 10.9 plus or minus 0.9, and then we have 11.3 plus or minus 0.8. So we can see that, overall, the track as a whole was relatively consistent. One end of the track looked like the other as we go around. And then we're also seeing that the inside racing lanes versus your outside racing lanes were also relatively consistent. So this is the question that everybody wants to know. Was it good or was it bad? How did your track hold up? Well, thanks to HISA facilitating, this data collection on a national scale, we went from going to about 15 to 20 racetracks to this year, I believe we will have tested nearly 47 racetracks. And so now we're starting to actually get some real statistical power, and we can actually sit here and show how does a track compare to industry ranges. So this is honestly really exciting and something that we've longed for, for years, is to have this data set. So I would like to preface that this curve here and these numbers that I'm about to show you, we're still in the beginning stages, but this is where we're starting to head to. And that is, how do you hold up to the industry averages and ranges? So we talked about the 3 measurements that we're taking with the OBST, your cushioning, your impact firmness, and your slide. And so we can compare those to the industry averages here. So this curve or box and whisker plot, sorry, shows each track. So in this case, we have 37 discrete racetracks. We're still processing some of the tracks. We still haven't tested a few this year yet. So that's why we don't see the magic 47 number on this. But we can sit here and see that each one of these box and whisker plots represents a single track. So the green here represents one standard deviation. The yellow represents 2 standard deviations, and the red represents 3. So cushioning, the average across the industry so far has been 10.8 plus or minus 2.7 kilonewtons. So we have our standard deviation across the average or across the industry as a 2.7. So what does that mean? I would expect to see that a track, if I were to come out completely blind and I've never tested your track before, that means I would probably expect to see that your track would fall between 8.1 and 13.4 kilonewtons. That's just the 10.8 plus or minus 2.7. And then if we look at the standard deviation across each of these tracks, we see that the industry average has had about, a typical standard deviation of 1.4 kilonewtons. So now I can have this basis. Are you within the industry range of 8.1 to 13.4? And do you have a standard deviation less or equal to that of the industry average? And so this is moving forward, how we're hoping that we're going to be able to sit here and determine, how is your track holding up, and are you near or at least within industry ranges, which is something that everyone has wanted to know for ages now. So we have slide 1.2 plus or minus 0.7 with a typical standard deviation of 0.3. And for the impact firmness, that's your peak decelerations. We have about 50.7 plus or minus 16.7 Gs with a typical standard deviation of 7.8 Gs. So, all right, so now that we have kind of a baseline of, how are we looking at the data, what is an example of what maybe would be good or bad compared to industry ranges? So I have 2 tracks here, one on the left, one on the right. Does anyone want to take a guess, which one would probably be considered good versus bad? Any takers? The left is good, right is probably bad? Yeah. And why would you guys say that? How? How is it more consistent? Right. Represented by the blue line. So here we can see that the grouping really tight. Most of the dots are on the red line, most are within the blue line. But, most of the dots are within the blue lines here on the right curve, right? But we can sit here and see that the standard deviation was plus or minus 2.2. That's nearly, 2.5 times that of this other track here, which is plus or minus 0.9. So we'll go into this a little bit closer here. So as you can see, yep, if we would expect to see the track was 8.1 to 13.4 kilonewtons for cushioning. This track came in at 11.9 plus or minus 0.9. So it's actually was within industry ranges, and that standard deviation was less than the industry typical industry ranges, which in this case was 1.4. So that's, getting close to nearly 50% lower than that of industry ranges. So that looks really good to us. We see the same with the slide. The track was 0.8 plus or minus 0.2. Industry range 0.9 to 1.5. Standard deviation typical plus or minus 0.3. Impact firmness, same situation. 34 to 67.4 Gs. We came in at 42. And the standard deviation was 3.2 for Gs for this track. And for the industry, that's 7.8. So across the board, we're checking off all the boxes. Yeah, this looks pretty good. So I gave you this good example, but would you guys believe me if this was the same track a month prior? No? It is. So, all right, I'm calling this a good and bad example because, when we're talking about looking at the tracks, we're mostly looking for, is the track consistent? That's the number one thing that we're looking at. So, if we're talking about consistency, standard deviation 0.8, that's still pretty good. Industry was 1.4, right? Slide 0.1, industry 0.3. Impact firmness ±3, industry range ±7.8. But if we're actually talking about the overall number, the average was 4.9. That's half, almost half of what I would expect to see. And this carries on for the slide and the impact firmness. So, the track was consistent, but it was, relatively on the low side. It's below what I would generally expect to see for a given racetrack. So what was the cause of this? Well, there was about an inch of cushion difference. They were running at about 5 inches. And so a month later, after we did the testing, we told them this, they worked on the track a little bit more, came back down to about 4 inches, which is how we got to, what I would call a good example. We fell within these industry ranges, the track improved, and it became more in line with the historical testing that we have done for the track. So, these overall numbers, the 11.1, the 0.8, the 42.6, that fell within their historical results as well, because that's the other piece that we're looking at. So here's our bad example. Is our standard deviation for cushioning within industry ranges? Anyone? 2.2, that's nearly double that of the typical standard deviation I would expect for cushioning on a racetrack. Slide was within industry ranges. The impact firmness was also within industry ranges. So that's good. And so now we have to come back and we have to look. Well, so obviously we have a large standard deviation. So that means that we have larger blue lines, so to speak. But we all have the quarter pole here. The quarter pole here was a spike. You can see that relative to the rest of the track, that it was it had less cushioning. That is, it would be maybe harder feeling. We had a few points out here at the 3/8 pole on the outside racing lanes that were actually really low. So what was the cause of this? A lot of it was driven by cushion depth. So we were lacking in cushion depth here, but we had too much cushion depth down in here. And so that led to a lot of the consistency issues that we see here, particularly with the cushioning. And so how is that fixed? Grading. And, maintaining that cushion depth is really important. And so we'll get to that a little more depth here towards the end of the presentation. So the next device that we will do for our on-site inspection is the ground penetrating radar. This uses radar pulses to basically pick up on reflections of your subsurface layers. So this is a lot like sonar, when you're like looking for the fishes, or you want to make sure that your boat doesn't bottom out at the bottom of your lake, as you approach the shore, perhaps. So each one of these dots represents a point collected by the antenna here. Cushion layer, base layer. This was actually radar performed on a synthetic racetrack. One of the other things that we can actually pick up on here is, your lateral drainage pipes. So as we come over it, we can actually pick up and determine where those are. That's represented here. I don't know if you guys can see it, but it has like these little hump shapes and they're stacked on top each other. So, what is the purpose of it? Just like the OBST, spatial consistency. One end of the track, it's got to look like the other. We want to see the inside racing lanes look like the outside. And also, of course, maintenance practices. Depending on what you're doing here, for a synthetic track, you want to make sure that you're not developing maybe a hard pan layer in here. So you're going to come in with that cultivator and you're going to break that up. We can pick up on that. We've actually seen on some synthetic tracks, when they get poor drainage, we were able to pick that up on the radar. And we could see that there was a subsurface layer that was developed and it was blocking the drainage of the track. So how would you interpret this? We present this data on a lane comparison, and we do it in a box and whisker plot. Ideally, what we would like to see is that each one of these plots is in line with each other. That means that we have no differences as we move out from the rail. So lane 1 would be right on the rail, lane 6 would be on the outside. As we move out, we would like to see that the size of these stay the same. We also want to see that the range is relatively small. So the range will be represented by these horizontal black lines. And then the data gets quartiled up. I won't get too much into that, but the orange line here represents the median. So we would like to actually see your median values and just be one line. We'd want to see the top of your ranges, one line, bottom, one line. These black dots are represented as outliers. So that would be, it's based on some statistical stuff, which again, we won't get too much into, but generally we would like to see, you know, a small amount of outliers like we do here on maybe lane 5 on the low end or lane 1, for example. So something that's really important when we're talking about ground penetrating radar is there is some limitations with how the data is calculated and determined for your depth. And so it's relative. We might report that the depth is at 2.56, but something to consider would be, well, did we test on an open track, that is, you know, the loose cushion, or did we test on a floated track, which would be relatively packed down? If you take a stick and you measure your cushion on an open track, you're going to get a different number than you would on a floated track, right? Because we compacted it down. So we would have a relatively shorter or smaller cushion depth, which would certainly be the case here at 2.5 inches. So that's just something to consider, that the depth, when we report it, it's relative. That does not necessarily mean it's the actual depth, but it's going to be generally within a 1/4 inch of actual depth. The other plot that we give you guys, what Branden also brought up, is a color map plot. One way to look at this is kind of like, okay, you got your rain forecast. I think everybody's seen those maps watching the Weather Channel, right? So you'll have green. Green will represent your light rain. Red would represent your heavy rain. Well, in this case, red will represent your relatively shallower. And then the blues and the green will represent close to the average. And then the blues here will represent, you know, that you're relatively deeper. So what we would like to see is that you have a uniform color. That would mean that your depth around the racetrack is uniform, and that we're not seeing like any relatively lower spots or any relatively higher spots. So this would be a great example of GPR. So just like OBST, we can actually sit here and look at the industry ranges thanks to HISA's facilitating this data collection. And we can see, you know, what are typical standard deviations, averages, et cetera. And we can apply those ranges and look at it just in the same fashion here. So example of good and bad. Let's do this again. Left, good, or right? Left. And why is that? Mostly in a straight line. Good, good. And you can see that the size of these plots is actually smaller than our right. So in this example, you know, we have a standard deviation of 0.2, keeping in mind that our typical standard deviation will be 0.3 inches. So we're matching that. This track has a standard deviation of 0.57. That's almost double what I would expect to see on a given racetrack. We're also seeing that we have what looks like a climb. So what this is saying is that as I move out from the rail, lane 1 to lane 5, we are getting relatively deeper. So that means that we actually have more material out here than we do in here. So what could have been a cause of this? Perhaps when they were going out with the grader, they may, a typical practice is to pull the rail, you know, as you harrow and as you get rain and everything, material can move to the inside, they pull it out, and they may have taken too much off of the inside racing lanes, and that could be a cause of this. So here's another good example that's even better, in my opinion, than this one. You can see how small this is. Straight line, uniform color, low standard deviation. It was 2.86, which is within industry range. And we had a plus or minus 0.2 inches as opposed to plus or minus 0.3. Here we can see that we have a relatively uniform depth all the way around as indicated by the color map. And here's our bad example. Here again, as we move from the inside lane to the outside, we're getting relatively deeper. And I love this color map plot because it really shows what it is that we're actually looking at here. We can see that as you enter this turn, that it's relatively shallow on the inside lanes, but we're relatively deeper on those outside lanes. And we can see that this turn is relatively deeper than the far turn. So this is really a great representation of the data, and it can actually show where a lot of your variation is coming from and spots to work on. So we could probably say that as you're coming into this turn and through it, that would be a good spot to come back. Let's check your grades, let's check your depth, and let's see what we're actually looking at and what might be potential causes of this. So the next thing that you'll see in your reports is the rail inspection designated by RH, and then the pole distance designated by PD. So we come out, we take the tape, we stick it on the ground, we run it up to the top of the rail, we get that rail height. But what we're also looking for is these gaps. We want to see that the rail is actually, in good condition and that it's safe. And if we see anything like this, we'll report it so that can get fixed. Pole distance, again, we're taking the GPS, we're marking the poles, and then we're going to be measuring those distances between the poles. So I won't get too in depth in here because it's relatively straightforward for your rail height. But again, we can sit here and look at industry averages. For a dirt track, I separated that out because the turf will have the movable rail, which is generally taller. ARCI and CHRB, they state that the rail should be between 38 and 42 inches. We saw the industry come in at 41.3 plus or minus 3.7 with this typical standard deviation of 1.3. So we can actually use this basis to see if your rail is relatively consistent as well. And we can do the same for the pole distance. Here, this is actually a good example of how outliers can skew with your data a little bit. Here, we're saying that the track is 65, or for the industry average, the tracks have about an average pole distance of 65 or 658.8 plus or minus 18.8 feet. But we have a few tracks here that have some outliers, particularly this one. And I looked more into depth in this track, and they had one of the poles, it was relatively too close and far. So we're actually seeing the distance between two poles right here because that pole was way off, which is good. So, that's something we're going to have to look at as we continue to look at the year or the data that we've collected over this year and reevaluate, which is why, again, I said at the beginning, I'm presenting you these numbers, but we're still churning through the data. But as we move into 2024, this is hopefully how we're going to be able to begin comparing everyone's tracks to one another. So we have the surface crossfall and grades, which will be one of the last things that we look at here. We want to be looking at the angle. We want to see that one end of the track looks like the other. As you're moving around the track, that you're maintaining that level of consistency. So what is the purpose of your surface and crossfalls? Well, there's several reasons for it. One is the water runoff. I really, really love this figure right here. This was on Arlington Park's training track. I remember I was walking out there and I saw this and I just had to take the picture. What I love about it is that it was raining, the track was sealed up, and you see these black lines here? That's actually your fines. And the fines create this great representation of water running off because the water is lifting it up and then pulling it out. So we can actually see this is the effect of pitting the grades on there. You're moving the water off the track on a dirt track because they can't drain vertically. They drain horizontally. I love this figure of it. Here we got an angle. This was at Del Mar. And this is just showing what I'm talking about when we're discussing crossfall. It's that slope, it's that angle, so to speak, on your straights. Another reason for having the grades, banking. When the horse is going around, it's going to be experiencing centripetal forces. And so to lessen the, the slip coming out like that, right? You put a bank on it, helps keep the horse more perpendicular or normal to the surface. So it's also a function of keeping the horse upright through the turn. And then as I discussed prior, with the radar, it can really affect your depth. So if your grade is off, it can actually change the depth of your cushion, depending on how you come out. There was a few of everyone that came out yesterday to Relito, and you guys saw the outside rail, right? And you could actually see the cement blocks on the outside rail, and you can see how we could see that it was relatively flatter. So if your grade is off, especially when you start from the ground up, if it's off below, as you move up, we can actually have a change in total material depth based on your grade alone relative to the base. So how are you going to interpret this? Yesterday at Relito, I had everyone cycle through and we took measurements, every 10 feet moving outward from the rail. It's important to note whether we are in the turn or whether we are not. Generally, your straights are going to be flatter than that of your turn because you don't need the banking in the straights. And then the banking there in your straights is a function of maintaining, letting the water flow off the track. So we're going to make sure that we differentiate between those. One thing to keep in mind is that when we're looking at the turns, we can have a transition zone, which I will let Roderick and Dean discuss a little more. And I have a great pictures to show of that. That's going to be different. So we try to keep that in mind when we're actually calculating averages. If you're in a transition zone, we don't want to necessarily count that as the average for your turn because it would be less than that at the top of the turn. So when we're reporting on this, we do every measurement that we take, 0 to 10 feet, 10 to 20, 20 to 30. That covers the primary racing lanes of the track. And we would like to see that the number is the same across. So here at the wire for this track, we had 3.1, 3.1, 3.1. They held that grade from 0 to 10 feet, 10 to 20, 20 to 30, and more importantly, 0 to 30. So we would like to see that these numbers are the same all the way across the board. So ideally, everything's equal, the turns are equal, but your straights wouldn't necessarily be equal to your turns. So again, we can sit here and look at how everyone's stacking up to the industry ranges. We see that the average for your straights is about 2.8 plus or minus 1.1. And then for your turns, we have 4.4 plus or minus 1.7. We know that a typical standard deviation for your turns will be 0.5%. And then for your straights, it should be around 0.4%. So what does an example of good versus bad look like? So here we can see that we're relatively uniform across as we move out, as opposed to the track here on the right. We're going from 2.1 to 2.7, 0.8, 1.5, 2.9, all the way up to 3.8. So you can see that we're not level, so to speak, as we're coming across the track. So for a good example, this is actually probably one of the best that we've seen this year so far. The track was 3.1% in their straights, plus or minus 0%, which is really impressive. And their design grade is 3%. So they maintained, their track within 0.1% of their target with 0% for your standard deviation. I find that really impressive. And the turns, they were targeting 5%. They were at 5.2 plus or minus 0.1%. really impressive to maintain that level of consistency in your grades. So what is an example of bad? Well, here we have track was in the straights 1.9 plus or minus 0.6. For industry, it was about plus or minus 0.4, so we're over that. For the turns, 3.3 plus or minus 0.8, with the industry at 0.5%. So we're above those industry averages and ranges for your straights and the turns. But I would like to point out more in depth the 5/8 pull here. So we went from 0.8 to 1.5. So that means we got steeper. And then we went to 0.8 and we went back to being relatively flatter. Well, that if your targeting was 2%, you're way off there on the inside here at the 5/8 pull. And then similarly, for this track, we had the 1 mile. The mile is not in a transition zone. So it wouldn't have been necessarily in between being what the straights and what the turns would have been. But we're at 2.9, 2.5, and then we jump up to 3.8 on the outside racing lanes. So, we don't see that the numbers are the same going across for each pull, and we don't see that we're maintaining that between the straights and the turns. So in summary, when you get these on-site reports, there's going to be a lot of data, and hopefully this presentation has hit a little more insight to what that might look like as we're going across it. Generally speaking, we want to see all the data is in a straight line, right? We want to see that everything's the same. That's what we're looking for. As of November 2023, these were the numbers, that we can sit here and begin to compare tracks to industry ranges and standard deviations, and we can really begin to evaluate where everybody's at and how you're holding up. So again, just keep in mind that these numbers are subject to change because this is just the beginning of that analysis, but this is where we're headed, and I find that really exciting. Do we have any questions?
So my name is Roderick Saylor. I work with GRW Engineers. I think I'm here to kind of discuss at what point do you want to bring an engineer into onto one of your tracks and look at rehab project or a rebuild. So I don't think I've ever been able to do one of these speeches, done a couple of them now, without kind of explaining where I came from and why I'm even here in the first place. I'm here, been with GRW for 20 years. In those 20 years, I got 19 years working with my mentor and predecessor, Harvey Helm. And one of his first clients, or GRW's first clients, was Keeneland. I think our project numbers are in the 6,000 range now. Keeneland was 100 something. So he had been working on tracks for his entire career, and I came along about 20 years ago and immediately kind of got to jump right into it. So we're a full service firm. I've worked on tracks from brand new facilities or things like Belmont, where we're kind of wiping the slate clean and rebuilding everything from scratch, down to rehab, which is I'm going to highlight one of the rehab projects that I got to work on the last year that I think was pretty neat, that I think gives you an idea of where we can be of assistance. In addition, our architectural services have designed some barns. We've done some rehab facilities, and then, for new facilities, access roads, utilities, things like that, kind of general engineering services. So when would you give us a call? So new or rehab projects is what I've referred to. New projects, pretty obvious. Rehab, are you rehabbing your base? Are you resetting your rail? What is the purpose of the project? And so the rehabs are, like I said, resetting the base. New tracks are your blank slate. You kind of get to do it, hopefully, do it right the first time, and kind of and think through the whole process, plan it out, and have it all laid out correctly. Before I really even come on to the site, we need someone like Dean, a surveyor, to come out and survey the site. GRW provides aerial LiDAR services. That's good for design purposes. It's not necessarily good to start checking grades on your track, but we do provide that, but for checking grades is where Dean or a surveyor comes in. But we can't start our work without having a good survey of your facility, of your tracks. In addition to that is either geotechnical borings and or GPR. I think we covered GPR enough a moment ago. I'll go over a little bit. Most of what I'm gonna highlight was done by with geotechnical borings on the track that I'll highlight here in just a few minutes. To help us kind of all speak the same language, one of the things that I've ran into the most is nomenclature differences. What do we call things? So we're talking about crossfall or cross slope of a track and how is that measured? In the engineering world, surveying world, planning world, it's tenths of a foot or percent. I hear it described as degrees a whole lot. What's the percent of what's the cross slope of your track? 2 degrees. Well, 2 degrees, if you look at the top chart here, 2 degrees versus 2% is a difference of 0.75 feet. So that means from your inside rail to your outside rail, you're actually higher if you have a 2-degree track. So it's a nomenclature thing, just to kind of for educational purposes. And then, as you go through, if you have a 4% track, then time you get to your outside rail, you could have, 50 feet out, you're 1.5 feet higher. One of the things that we incorporate into when we can, sometimes when we come out, we're doing a rail alignment project, or it's a rehab project that includes resetting the rail or placing new rail. If in those circumstances, the track is a simple curve. So you run on your straights and your turn is a simple curve with one single radius. That's generally some of the older tracks that we've come on to work on. What we try to include in that, if possible, for rehab projects, but definitely new projects, is providing a spiral curve at the beginning of the turn. And what that does is there's a couple items to hit on here. First is, I don't know who's got a pointer. The TS, SC, CS, and ST. That's a tangent to spiral, spiral to curve. When you're at the curve, that's your radius that you would normally call your simple radius of your track. CS is curve to spiral. Now you're leaving your regular radius into a spiral curve back into a tangent. And what does that mean for a track? Well, here the TS, the tangent to spiral, starts really 100 feet before a simple radius would normally start. So simple radius, a simple curve would start at the PC, the point of curvature, which is out this way. You're running a little bit longer and you start the turn later. The spiral curve actually pulls the rail in a little bit and softens that turn. It almost feels like a corner sometimes when I'm laying it out in AutoCAD or on paper. A simple curve feels like a sharper turn than what a spiral. The spiral helps you kind of ease into that turn. So this is something we try to incorporate into new tracks or rehabs when we can. Who's built a track just on their free time? This is a track that I built just playing around with AutoCAD one day, wanting to understand what would a perfect mile look like. And what it comes down to is you have a 420-foot radius, and the track here is equal lengths in all parts. So the turns, the straights are equal lengths. And in here, you'll see the items that we referred to a minute ago. You see the ST, spiral to tangent. This depends on which direction you're going. So you've got your spiral turn that goes for a period of time until you hit the CS, which is the curve, the spiral. And then the rest of this is a simple radius, the 420-foot radius going around the turn. When we're setting grades on the track, we are usually, when we come to a facility, the track super knows what he wants his cross slope to be, if it's a new construction, or what their cross slopes used to be and what they're trying to get back to. So what we will do, we'll start setting that and we'll measure, and I've got some cross section in a minute, I'll highlight some of that. But we go from 2% in the straight, and then what we incorporate the transition to be is through the spiral portion of the curve. So that first 200 feet while you're in the spiral will be the transition from 2%, in this particular case was a 6% cross slope in the track. And then you're in 6% full cross slope, full super elevation all the way around until you hit the spiral curve coming out of the turn and eases you back down to the 2% that's in the straight. The transition zone isn't always going to be 200 feet. It's going to really matter. This one climbed pretty good, from 2% to 4, or 2 to 6. That's 4 additional percent change. So really, that one needed to be stretched out a little bit. We've done synthetic tracks that go from 0% to 4. That's 4% again change. So that transition zone getting you from your cross slope and your straight to your turn needs to be a little bit longer. Otherwise, your outside lanes or your outside part of the track is really kind of climbing uphill in those situations. And then in all the scenarios, in a perfect world, your running line is flat all the way around the track. We do our best to keep that same situation. So the running line here doesn't see the effect of it going up and down. If the track is completely flat, you're on that. You're not climbing in elevation as you go around the turn. Okay, so this was an interesting project I got to work on this year, or in the last year or two. This color map is not the same as the one with the GPR, but it is developed based on borings and depth of base material. These track owners went through the extra effort of getting borings done every 50 feet in a cross section across the track. So from the inside rail to the out, maybe 4 to 5 borings, and every 50 feet along the rail, all the way around the track. So what that did was give us an opportunity here. Let me zoom in on that a little bit. We got an opportunity to see, they pulled the cushion off, did the borings. We surveyed the top of base. And then the borings gave us an opportunity to know what the depth of that existing base material was. And so you can see in many places, it was fair. This is an example of an area that was a thin on the base. Oops, wrong way. So the other objective to this was not just understanding their base, it was also giving a consistent cross slope on the straights and the turns. So when you apply a consistent cross slope, you end up with some other variations, and I'll highlight that maybe in the next slide. But what this gave us an opportunity to do is what they really needed to do here is they knew they had this base material, that's stuff they could save, pull that off, set it aside. But underneath there, they had to get to a new base layer. The black line on the bottom was the bottom of new base. That was really the part of excavation that needs to occur in that track. So they're going to pull that off, and that's kind of spoils material to take and set it aside or contract or truck it off. But they removed the base between the 2 red lines. So now the difference of what they needed wasn't a full new 6-8 inches of base, whatever it needed to be. It was really just you were able to target and pull out what was usable base and what needed to be replaced. So it was a way to really tighten up the budget and assist in that without it really kind of being a super expensive project. Prior slide showed the difference of when they were measuring cross slopes, how it changed from 2%, 5 feet out to 10 feet out, and maybe 1.9 to up to 3. The bottom red line is existing track. And this kind of highlights what you would see there. And I'd almost expect on the bottom left here, you would see ponding water right at the running line, kind of right there where it says EG 2802, that's the elevation there. Just simply because it's bottomed out and it kind of starts climbing up grade as it kind of comes to the inside rail. So here is an example of a track that needed kind of to reset the entire base and cushion and reestablish the cross slopes. So, and that's, you can kind of see that occur in both places. You can see the bottom red line on the left tried to have a crown. Maybe in the original track when it was built 30 years ago, it had a crown. But in this particular case, years of maintenance, maybe the crown wasn't in a consistent place and the maintenance folks had a hard time kind of keeping it in location. It kind of wore itself down over the years. Another similar situation, resetting the track, surfaces, and then just a couple more examples. These two here, are the same. The bottom is a little bit more blown up. The black dash line was their bottom of base, the bottom existing base. The red dash line was the top of their existing base. So as you can see, some places the base was very, very, very thin. Other locations, they had way more base than that they needed. The ultimate result in this particular cross section was taken in the beginning of a transition of a turn, 3.38%. but we averaged that out and tried to tie in our grade in a rehab situation. We don't want to reset the rail if we don't have to. Try to tie the grade in on the inside and try to really come close to tying in on the outside. And usually in that case, the board's going to make up the difference if I've got a cut situation. In addition to worrying about your consistent cross slopes, we look at what the consistency of the running line is. So these are profiles. If the horse or person is walking, running along the running line around the entire track, what does the track do? So in this particular situation, the existing base is the dashed line, and you can see how it kind of meandered up and down. So as you're going, not only do you're worrying about cross slope, being consistent, the running line also needs to be consistent so that you're not up and down as you're going along the track. This bottom example here too had a little bit of a peak in the track. So this one we took a little bit more effort to put more earthwork into it to remove a big piece of that and flatten that out over a period of time. So these are just kind of examples of where we've come in and rehab projects from an engineering perspective. We worry about the alignment. We worry about the cross slopes being consistent both in the straights and the turns. Looking at the depth of base, is the base consistent all the way around? And stormwater drainage and make sure all the water gets out and away from the track.
Good morning. My name is Dean Johnson. I'm a licensed land surveyor from California. Don't hold the California thing against me. Probably not too many Californians here. What I'm going to be, everybody can hear me okay? What I'm going to talk about is more equipment that you're going to need or should have, and laying out these transitions here. If you're regrading your track or you're just trying to maintain it, it's important that you get these transition cross slopes in the correct location. First off, in all the previous presentations here, we have a mixture of inches and tenths and hundredths of a foot. And I would highly recommend that your staff find one of these pocket tapes. This is an engineer's pocket tape. This one happens to be 25 feet long. And on the top, the foot is divided into tenths and hundredths, and the bottom is in inches. So we have the top of rail to the top of cushion is in inches, the depth of the cushion is in inches, but all the slope calculations and the laser level measurements are in tenths and hundredths. So this is just real convenient to convert from inches to tenths and hundredths, or from tenths and hundredths to inches. And you can find these at any surveyor supply store, or even online. Home Depot used to sell these. I don't think they do anymore, because it's just usually surveyors that have these. So I'd recommend that you guys get one of those. Now, when we go in to regrade a track, whether if we're regrading the base or regrading the cushion, we need a laser level out there to measure what the existing slope is and set stakes for what the slope should be. And so one of the first things I do is I go around the inside of the track every 1/16 of a mile, and I measure down from the top of rail to whatever that depth is to the top of the cushion, whether it's 41 inches or 42 inches or 40 inches. I measure down, I set a wood stake that's exactly, let's say, 41 inches from the top of the rail. And that's the beginning point for regrading the track and maintaining the track, is you have to have that set elevation from the top of rail to the top of the cushion. And then from there, the grader can start grading out in this particular case, 3% in the stretches and 5.5% in the turns. So to help with the transitions, I use this high-tech method of a paper plate, a Sharpie, and some packing tape, and I mark what the percentages are. And then in this particular case, we're changing 1/4% every 30 feet. So I measure along every 30 feet. I mark on the top of the rail with the Sharpie what the slope is, and then I tape one of these paper plates to it at that point. So when the grader comes along, they can just look down, they can see where they're supposed to be, and they can adjust the grader cross slope to match these slopes. That way they precisely can get the grade correctly. Others have actually made plates made up that attach to the rail with these numbers on, but this works very well unless it rains or if the water truck comes by and sprays it with water, and then the tape comes off. But this works really well because it's important to maintain these cross slopes. I think pretty much that's sort of what we do when we're regrading or maintaining a track. And I just want to stress how important it is that the tracks have a laser level, and somebody who's trained in using them and how to do the calculations so they can determine what the existing slopes are and do any staking to get to the correct slopes. And then once it's regraded and they're maintaining it, you're going to need somebody out there that knows how to use the laser level along with calculating the slopes to maintain those slopes. And then you maintain them, you're not going to need to go back and have to regrade it and shut the track down for a couple of weeks while it's being regraded. So it's important that we have the track maintained. I think that's about all I needed to say. Is there any questions about anything? Okay, great. Thank you.
Yeah, and Dean, yesterday, we worked with a number of the folks out at Relito yesterday and was training them with the lasers. So they finished with that.